Hi, my name is Lenny. You can just call me Lenny. I work a lot with modernist architecture in Brazil. We have a big problem with all of modernist architecture because it's reaching the end of its service life. So it's mostly built out of reinforced concrete, and Brasilia is a huge city built pretty much only out of reinforced concrete, and so many beautiful national heritage that it's way too recent. Our national heritage is very recent. So my project, I wanted to join the visual analytics possibilities of BIM and the predictive simulation scenarios of the Ross-Heideck method, which I'll explain later, to do facilities management in modernist architectural heritage. So our first modernist buildings to be considered national heritage were that's the San Francisco de Assis Church in Belo Horizonte, and this is the MESP building, the Capanema Palace in Rio de Janeiro. And the first one was built in 1943, and it was considered a national heritage only in 1947, so it was very, very young. And the MESP building was built in 1945 and considered national heritage only 3 years after 1948. So at that time, we didn't have a lot of research on durability of reinforced concrete, because it was a fairly new material. And when it was firstly built, people thought that it would be eternal, I guess. They compared it a lot to stone, so they thought that as long as the reinforcement was inside of the concrete, it would be eternal. They didn't have a lot of research on service life and on how long these buildings would last. And now we know that they're reaching the end of their service life. The Brazilian NDR, which is the Brazilian norm, it gives 50 years service life to reinforced concrete. It's too little. I mean, almost all of these buildings have surpassed it. So we're actually taking into account the ISO and the Portuguese norms, which gives it 100 years, but it's still not enough. So we need to be able to analyze these structures and see what needs to be done and how they need to be conserved. The problem is almost all of these structures are government maintained, and the government doesn't have an annual maintenance budget in Brazil. So, preventive budgets. We have mostly reparative maintenance and almost no preventive maintenance. So we need to figure out a way to make it, we need to make more tools to be able to analyze and convince people, facilities managers, to maintain these buildings. Brasilia was built in the end of 1950s. It was inaugurated in 1960, and it was a big symbol of nationalism at the time. The Juscelino Kubitschek government wanted to make a city that would symbolize our national heritage. And that is why most of the buildings were so young when they were considered national heritage. So we can't really do anything with these buildings. We can't knock them down. We can't change them because they are landmarked. But we have to. They don't appreciate the importance of preventive maintenance. So in Brazil, what we have is a few levels of preservation. We have the United Nations, which is the international level, the national level, which is IFAM, which was only created in 1937. So that's very close to all of these modernist buildings. And the reason why modernist buildings were considered national heritage is because most of the architects that built and projected and designed the modernist buildings were working for IFAM. So most of our, in most countries in the world, conservation, architectural conservation walked separate from architectural design, but in Brazil they really came together and worked together a lot. And as a regional tool for preservation, we have these I don't know, I forgot the name. It's like these inventory files, and it's pretty much just written information. So we're seeing that it has a huge potential for HBIM in that area, because we need to get all of this information on all of these structures, and it can't be just written information. We need a lot more. We need digital information. So that's a little bit of why we're researching what we're researching. And we use a lot of these degradation and depreciation analysis of buildings, where this is kind of where the research came from, is the calculation of the depreciation. So in economic factors, depreciation is linear, mostly calculated. If you have a building that lives 100 years, he will be depreciated in 50 years, half depreciation. So that's not how it works. That's not real life. I mean, buildings that were built at the same time can have different depreciation statuses. So all of these formulas kind of evolved to represent a more realistic depreciation method into the Ross-Heideck and expansions formulas. So we take the actual age of the building and the estimated service life, and then do all these calculations. And the really important thing here is the depreciation status, which is right there. So it's mainly based on a visual inspection of a structural expert or a building expert, or whatever the kind of elements. So a facade expert, a window expert, he will give you a conservation status of the building, and then you can calculate how much it has depreciated. And this is a big part of our study, because it's very subjective, and we're trying to make it a little bit less subjective. So we're using a few other formulas, the deterioration formulas, such as the GDE of Winnipeg, was created by my university, and the Dutch standard, to better inform this depreciation status. And a few other researchers in Portugal, like Pimenta and Pereira, they have also contributed to this formula. The first, Pimenta, was contributed by adding different elements. So instead of giving a conservation status to the whole building, you would give conservation status to different elements, and then make a weighted sum. And Pereira works on the estimated service life with the standard service life. So he put all of this information into it, like project quality, execution quality, internal environment, to better understand the estimated service lives, instead of just the standards, what the standards say that the building should be durable. So what I did was put all of this information and scripted it into Grasshopper, Rhino Grasshopper, and I work with a color to present how these buildings can be depreciated, how they were depreciated, and all of this is my scripting. And then, like I said, I'm trying to work with all of these other formulas. The GDE formula takes into account the 2T graph to calculate the deterioration of the building. So at the first 60% of its life, it doesn't deteriorate as much, but as soon as it reaches this point, it will start to deteriorate very quickly, and it gives us a more a less subjective depreciation depreciation scale for the scale. Also, the problem is the GDE, it's only for structure, and Ross-Heideck can analyze any building elements. So we at the university were trying to figure out how to bring the GDE into other building elements, not just structure, but windows, facades, and everything else. This is the Dutch standard. The Dutch standard is based on the critical rating factor. So instead of analyzing, the GDE is based on importance factor and ponderation factor. So a ponderation factor would be what kind of problem the building has, or as, for example, the reinforced concrete would have like a crack, so that would be one ponderation factor. It would have efflorescence, which is another ponderation factor. So we use the different ponderation factors, and the intensity factor is more visual analysis and attributed by a specialist. However, the Dutch standard is mostly based on visual analysis and the volume of the respective defect. So if there is efflorescence on just 10% of the elements, it will consider that into the calculation. So my use case is in Brasilia. That's the city I live. It's right in the middle of Brazil, so we don't have a lot of beaches there. And in Brasilia, that's the projected city, modernist city in Brazil. This is where the university campus is located. It was supposed to be located a little bit closer to the center, but people were afraid that the students would be a little bit too much trouble for the government. So we're located right there, and okay. This is the Central Science Institute of the University of Brasilia. It's 720 meters long, and this is the architecture part of it. So it was a big project of Oscar Niemeyer to integrate eight colleges into one and have all this integration between students. And it's a huge step for prefabricated structures in Brazil. I mean, it was one of the first, I mean, the second or third building in Brasilia to be prefabricated, except the problem was it was prefabricated, but the fabrication was on campus, so it wasn't very good quality, and now we're getting a lot of problems with it. So you see, this is the ceiling of it, and it's pretty badly damaged. And the pillars, you can see a lot of the concrete is what do you call it? Well, there's a lot of efflorescence and a lot of the word just went straight out of my head. Well, anyway, you can see a lot of the problems of the prefabricated pillars and the problems of the roof. And okay, so what I did, I went into Grasshopper, this plugin of Grasshopper, and divided the whole structure. This is one element, one structural section, and I divided it into finite elements. Still not as much as I would like, because of my computer ability to process these elements, and then mapped all of the problems that we have, the pathologies that we have, and mapped them into each individual pillar and beam and slab. And in the case of the original work, I was supposed to add the windows and the rain gutters, but it just became too heavy. And this is kind of how I mapped it. So I used the scale from green to red. I don't know the time. Oh, okay. So I used the scale from green to red to map the degradation, and then showcase how it would get better with time and with the different scenarios. So, for example, if I would just add more preventive maintenance, give a better rating for preventive maintenance, all of the all of the degradation would get better about 5%. If it had preventive maintenance all throughout its life, it would be worth 5% more. And if, for example, if you change the windows and the rain gutters, substituted them, it would be another 5% more. And if you did both, another 5% more. So that's kind of what we're working on, all of the simulation. And this is how I. This is the GDE. the ponderance factor, the importance factor, and that's the formula that I showed you earlier, and so this is what we use to give a rating to each element, and each element within the element, each block within the element, and then calculate the volume and how the volume affects the whole structure. So this is, you can see the yellow lines here, those are the pathologies, and you can see this is the first one, like this is the pathology for the GDE, and this would be the pathologies for the Dutch standard. And you can see the difference is because the Dutch standard takes into account the volume and the GDE doesn't take into account. So this is just a little bit of what we're working on now. And okay, any questions?
So as a big fan of Modernist buildings in Brasilia, especially in Brasilia,
Yeah.
I really enjoy the talk.
Thank you.
Does anyone have a question or comments? Which can help?
Yeah, I think firstly it's really great to see such contemporary technological tools being used with historical buildings. I think that's fantastic. Just sort of a combination of things to see and talk about. You showed the crystal add-in for Rhino Grasshopper there, and I was just wondering what that's doing within the project.
Okay.
What part does that play?
Yeah. So this plugin, it divides. You can. I don't know if you're familiar with Grasshopper terminology. It divides a B rep into a determinate amount of voxels. They call it voxels. So it will divide it into, for example, 10 by 10 or 5 by 5 voxels, and then I make like a cube around each voxel to calculate the volume of each voxel. So I separate the pathology, the little different pathologies inside the element by voxels and inside the element. So it calculates it by itself. I don't have to divide the actual element. It makes it for me.
That's the reason the computer became really slow.
Yeah, exactly.
Everything.
Exactly. Yeah, it's very hard to process. It needs a very good computer, so that's kind of one of the problems we're working on.
Yeah. Any other comments? I have a quick comment. I think it really precious because you said the government has a limited budget and they need to prioritize which one should be maintained first. So if you can come up with some numbers for every building, it would be really, really, really great. But one concern I have is probably they need to spend more time on building the modules first.
Yeah,
so
I agree.
They are limited in budget, and how can they make buildings determine outcome? And another one was that you had many variables for different, for quality, to measure the quality of different things.
Yeah.
Then that means that you need more money to hire examiners for different aspects of a building. So is it really?
Yeah, since the universities of Brazil are mostly federal universities, we usually use students for that, graduate students. So instead of using graduate students for companies in Brazil, we just use it for government. So we'll put a lot of students just to do all of that. Usually that's what we would do, like make the BIM models, and yeah, that's sort of what.
I think it's worthwhile keeping teacher market where they train of the famous buildings.
Oh yeah, no, it's definitely worth it. Yeah, and it's a necessary step. This is just one little part of the whole research. So a lot of us are trying to make the digital models of the building. So this is just one contribution to it.
Yeah, great.